This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Make sure that's on. Oops. Okay. Let's get started. Thanks. Cool. So today's lecture, we're going to move on to another topic, which is getting more into the level of words and the semantics of words. In this class, we're not really going to go into semantics much beyond the level of words, but bear in mind that there is a massive area of research in this space, and this will be a little taster into it at the level of words, which is becoming, as you will see in the next lecture, start talking about the models that you may have heard of before, words as vectors, word2vec, and various other technologies which are starting to make a very big splash out in the general world beyond the field of research. So in this first lecture, we'll talk more about structured resources, and in the next lecture, we'll talk about how we learn these things automatically. Okay, so first to motivate, I'll just start with revisiting this classic text classification problem of sentiment analysis. And if we consider this situation where we have some training data, so in this case we have 3 sentences, 2 of them are positive, 1 is negative. It's a slightly toy scenario, but bear with me. If we now see another example, this is a wonderful film. We have to try and decide because it's a simple scenario, we can kind of figure it out ourselves, what the classifier would predict. And notice here that were we to use bag of words, right, what is the similarity between the words in our test instance versus our training instances? You can see here that this is common to everything, so one expects we might throw that out. It's an uninformative piece of information. So now we're left with good movie, great movie, terrible film versus wonderful film. And you can see here, what we're going to find out is that it's negative, right? It had the word wonderful, but we don't know what wonderful means because we've never seen it before. It had the word film. We think we know what that means because it happened in one of our negative training instances. So we'll be quite confident that this is a negative tweet. Okay, that's not the best because actually, as we can tell from reading it, it's quite positive. So the problem is the model doesn't know. Nothing is contained inside of this system to say that the word movie and film are synonyms. They mean roughly the same thing. And it's just treating it as a word. It's an identity. If it occurs in one of our data points, then we treat that as evidence for that word being potentially good or bad, depending on the label of those instances. So it's not learning to aggregate over this. And similarly with words like wonderful versus great, they might be the kind of things that we would also think to be roughly synonymous. If we had that information, then we'd make a very different outcome in our classification. Okay, so wonderful is not in the vocabulary. This is what we call an out-of-vocabulary word. We're not going to be able to process it unless we have some other information. So what we'd like to do is to add some semantics to the model. We'd like this approach to know some more information about our lexicon, to know that these words are linked, to know that they're synonymous, or to know that their meanings have some overlap, for instance. Okay. So let me remember where I'm getting at with this. So if we're going to compare all these words directly, it's not going to work as described. So what we'd prefer to do is compare the word meanings. And the way we're going to do this today is say that we have some lexical database. So when I say lexical database, you can think in your head's dictionary for the moment, and it gets a little bit more nuanced than the dictionary, but by and large, the basic idea is similar to what you find in a dictionary, right? You'd find a dictionary definition for film, you'd find a dictionary definition for movie. They're going to be quite instructive to understand that these words are similar to one another. So in general, we call this a lexical database, and I'll give you some examples of lexical databases other than just dictionaries. Okay, so word semantics, it's a very broad field. This lecture, we're going to cover the idea of lexical semantics. So this is the idea of looking at the meaning of words, how the meanings of words relate to one another, and specifically through using a lot of these hand-annotated resources, these things like lexicons, thesaurus, dictionaries, and more generally, this idea of an ontology. An ontology is when we take these resources and we create, for instance, a big graph out of them to say that words are nodes in graphs, and we'll have lots of different types of edges rather than just some fixed inventory of words with descriptions, as you might see in a dictionary, for instance. Now, the next lecture, I'll talk about distributional semantics, and that's how words relate to the usage that they have in text. So, for instance, if you'd never heard the word film before, imagine you're a second language speaker learning English, you know the word movie, but you've never seen film. If you were to read it and see that word several times in some text in English, you could probably figure out what it means just by looking at the contexts. So seeing that people went to this, who knows what, certain actors were portrayed in this item, and so on, gives you a whole lot of clues because they're the kind of things that would occur for movie as well. So that's what we'll get to in the next lecture, talking about how we can get those intuitions of trying to sort of figure out by looking at words in context and looking at the different contexts that a word occurs in to try and figure out its meaning. And this is a way of kind of automatically creating these meanings, and people have used these in the past to automatically create lexical resources like thesauri and so forth. And in fact, that's how dictionaries are created in the first instance as well. People looking at instances of words in context and trying to deduce their meanings. Okay, so first the question that we'll look at is, what do words mean? This is quite of a tricky problem, and it's a general problem of semantics. So if we were to be in a course within linguistics, you could talk for many lectures on just purely what is meaning, what is the meaning of a word, what is the meaning of a phrase. And one standard, fairly robust mechanism for characterizing semantics is the idea that words might mean some item in the real world. So we might have the idea of a laptop is this specific object. So when I mention laptop, I'm talking about this one. We might be talking about the class of laptops, which is a larger set. And when we're doing various operations in language, we might be reducing that set, say by doing set difference, set intersection, and so on. So, you know, the green laptop, for instance, will help to disambiguate between the larger set of laptops and a set of green laptops, say. And various operations can be thought of as operating over sets of reference. Now, I mention this just to illustrate that there is a underlying sort of theory, underlying semantics, and there are a whole lot of different theories, and particularly how semantics is built up over larger text structures. Now, usually in text analysis, we sort of are a bit more theory agnostic, and we work in a more simplified setting. So, in which case, we use a more grounded, more easily automated kind of mechanism to represent semantics. And one particular reference might be its dictionary definition, which is a lot more concrete, because if we have a dictionary, we can search for the term, we can look up its definition. That's great. The problem here is that dictionaries are written for humans, not machines. If we look up the dictionary definition for a word like green, we'll get, let me just see, I just did this before. If I can. So I'm looking up in WordNet. We'll see WordNet in a bit more detail in the next few slides. I searched for the word grass. Did I? Wait a second. No, I didn't search for it. I didn't hit enter. I searched the word grass, and I get narrow-leafed green herbage. Maybe herbiage? Anyway, maybe that's an Americanism. And then, so in order to define grass, we use the word green. If we look at the word green, we're going to find the word grass in the top definition here. So green color or pigment resembling the color of growing grass. So there's a classic example of a circular definition. If you don't understand the word green, it's kind of hard to understand what grass means or parts of the definition. If you don't understand what grass is, it's kind of hard to describe what green is. So dictionary definitions are often circular, which makes them difficult to work with. Let me see if I can find where I was. Yes. If we understand a little bit of the meaning, then that's okay. We can then bootstrap and learn other things from a dictionary, and that's usually what dictionaries are written for, right? For humans who have some level of language understanding, and so then they can understand more advanced concepts that they may not already know. Okay. But given that, we're still going to look. We're going to see how we can use these kind of resources. And in particular, the key resource that we can use from dictionaries or similar lexical databases are the idea of relationships between words. So if we know that the word green is a color term, much like red and yellow, that's a piece of information that might be quite useful in doing our text analysis. Okay, so the idea here is that we're going to look at words and their senses. So if we look up a word in a dictionary, we're going to see a reference to it. So in this case with bank, it's a noun. It can also be a verb. Here we're just looking at the noun. We're going to see a whole lot of numbered definitions. So number 1, bank is a financial institution. And then there's a semicolon and there's another sort of variant. So a building where a financial institution offers services. So you can talk about Commonwealth Bank. You can talk about the branch of Commonwealth Bank, as in the building that you go into to do your banking. Both of those can be described as bank. So I bought shares in the bank. I went to the bank. Both of those are fairly valid or perfectly valid ways of describing it. They're describing slightly different semantics, but by and large the semantics is very similar, and that's why they've been grouped together under number 1 here. It can also mean, so you can, as we get towards the end here, a repository, a container for holding money. These are getting a little bit further away from the idea of a building where they trade, where they give you money or you give them money, depending. But you can see that it's related. There's sort of they're all to do with the dealings of money and deposits and loans and so forth. So the idea here is here's a couple, more than 3. I've shown 2. These are showing a couple of different definitions for bank, and these are what we call different senses. So we have a word or a lemma, bank, and we have many different senses for it. And 1 and 2 are what we call homonyms. So the idea is that they're written the same, they're spelt the same, they're pronounced the same, but they're different words. We also, there's the term you will come across, homograph, which is another way of saying roughly the same thing. And now I'm trying to remember the other term. Yeah, sorry, homophones. So you have words that are written the same but pronounced differently. They tend to be different words, and they just happen to have the same spelling because of some random coincidence of English history. Same, of course, occurs in other languages. English is perhaps particularly bad in this respect, with Germanic language plus French influences plus a whole lot of borrowed terms from a whole lot of other languages of Europe and further afield. Okay, so sense 1 and 2 are homonyms. They're different words. They just happen to have the same spelling. And sense 1 shows polysemy. So what we mean by polysemy is that there's this fine-grained distinction. The words are roughly got a similar semantics. They probably derive from the same term if we rewind a few hundred years. Maybe they got borrowed from Danish back at the same time when there were Viking invasions, for instance. And since then, the usage in English has sort of diverged, and there are a few different meanings that are attached to the same term. But by and large, they're expressing similar semantics, and we call this polysemy because they're very related to one another. Okay. Okay, so there are various basic lexical relations. So hopefully this is visible to you at the back. I can put it on this thing if it's more visible. I might do that anyway. But oh yeah, very visible. Is that? Is it going to wake up? Oh, yeah, okay. What did I turn off? Oh, there you are. It's better without the thing. Okay. So what we see here is, this is basically showing a fragment of various words, a fragment of WordNet. Notice here there are various different types of edges that are linking them together, and these are the relationship between words. So, for instance, we have a fairly generic term here, person, and then a specific type of person is here, a relative. A specific type of relative is brother and sister. So this is like the is-a hierarchy that you see in UML and so forth. So these straight edges with arrows are basically saying that this child word is a version of the top word. And that's what we call hypernyms and hyponyms. So hypernyms are the generic ones, and hyponyms are the specific ones. So the E is closer to the start of the alphabet, so it's higher up, and the O is closer to the end of the alphabet, so it's lower down. Anyway, you can come up with whatever mnemonic you want to remember this. It's kind of important because it can be confusing otherwise. So the backbone of this kind of lexical graph is this idea of these is-a relationships, hypernymy, hyponymy, which is just the inverse of one another, whether or not we follow these edges going up or whether or not we follow them going down. There are various other relations. So we have this little dash line here showing antonymy. So I'm sure you'll be aware of this. You know, you often see this in dictionaries as well, saying, you know, the complement of brother is sister. So it's not kind of, you could call it the opposite, I guess, being very loose with your language. It's a word that means something different, but it's kind of the logical complement. In which case, there's one here shown. We might show some examples later as well. The other type of relation is the part-whole relationship. The idea here is that an item that is comprised of several different things. So a car is made up of several wheels. It also has, you know, a dashboard, a steering wheel, seats, and so forth. Right? We'd use these curved arrows in this case to show that. So that's called a meronym or a holonym. That one's a little bit harder to remember because it doesn't just have one character distance, but they're just the opposites. They're just the complements of one another. So holonyms are the source of these curvy edges. Meronyms are the targets of these curvy edges. And you can see here that a person is comprised of a body is comprised of at least one arm, at least one leg, and so on. So this is like I can't remember what you call it, but there's a UML edge for this as well. So the idea behind this is not that dissimilar to the kind of stuff that you see in kind of a UML style graph as well. So this is just a snippet of the kind of graph that you'd see, but of course the data set is a lot larger than that. So let me flip back. If there are any questions, just interrupt me. Okay. So the database is a bit bigger than that. There are more like, I don't know, order of 200,000 things in this data set. 120,000 nouns and fewer instances of various of the other parts of speech. So it's largely based around nouns. And it's very rich. It's been developed for the past at least 20 years and gradually, incrementally improved to add more senses, more words, more senses, especially as new terms arise, like things like hashtag and so on. They weren't in the lexicon 10 years ago. They are now. And these kind of things gets included into WordNet. Oh, one extra thing that I should say before I forget. If you go back to here, one thing I haven't shown you here is synonyms. So in any of these one nodes, you might actually see multiple words. In this case, there's none illustrated, but for instance, flesh versus meat, for instance, you might have the two of them in one node to say that there are two different words that you could use to describe this concept. And so typically, each of the items in WordNet is a sin set. A sin set is like a circle in that previous graph. So the nodes then are slightly generalized. They're not words, but they're meanings. Each meaning can be realized with multiple different words. And a single word can be attached to multiple different meanings. So it's actually quite general. So I've got some examples on how you can use this. So it's kind of quite cool because you can interface with it directly using NLTK. So you can basically say, here's my query term, my lemma. I'm going to ask it to tell me all of the sin sets that contain this word bank. And it'll give me this list of all these things. These are different sin set objects. From each of those sin set objects, then you can extract a whole lot of information. So, for instance, we can look at the definitions. So the definition of item 0 is a piece of sloping land, especially beside a body of water, like a river, for instance. And then the second instance, we're looking here and we're saying, well, of this sin set, which has this horrible name, depository financial institution, it has various different ways that you could describe it in language. So this is an example of a sin set with multiple lemmas. Okay, hopefully that makes sense. There's a notebook that you can use to play with this yourself. The other way that you can play with it yourself is using this interface that I was just showing you before, where you can basically type. So this is just a web version of the same thing. It just presents things kind of, whoops, B-A-N-K. I can't see this in front of me, so you can see here. Here are the first two examples that we were just looking at before. And when we asked for definition, we got the bit in brackets. There are also examples. And if you click on this, I think you get a whole lot of crazy stuff. Yeah, so now you can play around with it and you can look at all of the hyponyms. So a bank can be a riverbank or a waterside. We can look at all of the hyponyms. And as we're going up, and you can see at the top we get to a really generic thing called entity, physical entity, object. These ones are a little bit uninformative, but as we're going down we get things like geological formation. So you can navigate it this way. You can navigate it in code using the API through NLTK. Yep.
That has been developed by hand?
Yes. Great pain and many hours went into this. So largely from looking at corpus evidence, so actually reading through various texts like newspaper articles, whatever else, and checking and saying, well, from what we have already, can we associate this instance of bank to any of these examples that we already have? If not, we're going to create a new one, we'll tag it, and incrementally over the years, then the resource got bigger and bigger. But it's largely a small group of people doing this really quite difficult annotation exercise. So yeah, there's a corpus called SEMCORE, which is the data that they annotated in order to create WordNet, which actually has the labels on each word in context. Where did it go? Here. I should just mirror my desktop so it would make it easier. Okay. So wait a sec. So we can look at other things. So for instance, we can actually look up lemmas. There's some weirdness, I won't go into it, of the WordNet interface where some things are defined on synsets and some things are defined on lemmas. Antonyms are defined on lemmas. So you can have a play with it and try and understand why. I'm not sure I really understand. But if we look up the word sister, we can ask for the antonym and we get the word brother. So, and this is pointing to a lemma. We can then ask that lemma, what synsets do you belong to, and so forth. So we can navigate around this graph very easily. Okay, we can call for hypernyms, we can call for meronyms, and so forth. So there are methods to basically work out this connectivity, the adjacency structure of this graph by querying from nodes. Okay, so now that we have this WordNet, this nasty, well, this lovely, big, complex thing that someone spent a lot of time creating, how can we actually use this in a practical scenario? So one way that we can do this is trying to look at this as a distance metric. So if, like our motivating example before, right, we're saying we had film and movie. If we could come up with an automatic way of saying how similar are film and movie, then perhaps we can use that inside a practical system. And so that's what we're going to be getting at here now. We'll talk about how we can get to looking at graph distance as a way of measuring lexical similarity. So we want to go beyond just looking at something simple. So words like money and nickel are related. This is an American example, nickel being their 5-cent coin, is it? I don't know, 5 or 10. No, that's a dime. I think it's a 5-cent coin there. So we'd expect that to be encoded somewhere in the graphical structure. It's not that obvious just from looking at the strings, and it's not that obvious from looking at corpus evidence, perhaps. So given WordNet, we're going to try and look about how easily you can get from one to the other by going up and down the hypernym tree. Okay, so it's going to look like this. This is our tree that includes both, well, this is a snippet of the 120,000 nodes, of course. So we have the word nickel here. It's a type of coin, which is a type of coinage, which is a type of currency, which is the type of medium of exchange, and so on, and going all the way up to very generic terms like standard, which, and then we can see here money exists here, and just for illustration, we also have Richter scale out here, which is how you measure how strong an earthquake is. It's just included here to illustrate that this is a very different term. It's got nothing at all to do with nickel. And we can see from the path lengths, right, that there's some evidence here. As we get longer and longer path lengths, we get more and more different meanings of words. So we calculate path length by adding 1 to the number of edges we have to traverse to get from one to the other. So getting from nickel to nickel is path length 1. Getting nickel to coin is path length 2, because 1 plus 1 edge. Nickel to dime, we go up once and down once, so 1 plus 1 plus 1, we get to 3. And you can see here, getting from nickel all the way up to here and down, we go up 1, 2, 3, 4, and down 1. So that's 5 edges we take plus the 1. We end up with 6. So that's how those numbers have come about that are illustrated there. And typically what we do is we talk about the path similarity. A very basic method of path similarity is just saying we reciprocate the path length. So now we get a number that quantifies similarity. We can see that if it's the same word, it's going to have similarity of 1 under this measure, because the distance is 1. If it's very close, like nickel to dime, it's path length 3. So we get a similarity of 1/3, and so on. Okay, so nickel to coin is 0.5. Nickel to currency, we have to go up 1, 2, 3 edges plus 1, so 4. Here's a quarter, and so forth. And money is 0.17. So now we have some measure to quantify how closely related these words are. And nickel to Richter scale is a bit lower, right? 0.13. Now, you might notice that this is a slight, there's a bit of a problem here, that nickel to money is reasonable, nickel to Richter scale is pretty stupid. It doesn't come about so clearly in the numbers. Obviously, there's a ranking, and the ranking makes sense, but knowing where to draw a threshold about where to stop in terms of similar enough to be useful is kind of difficult. And if we go through this top node standard, it's fairly bleached of any information. Okay, so the problem is that the edges vary in the actual semantic distance. So there are much bigger jumps near the top of the hierarchy. Yes?
And that looks like you are able to jump through any of the relations.
You're only jumping through the ISA relations, so the hypernymy and hyponymy. The problem is that the antonyms, well, the antonyms are not going to be that useful, but meronyms and holonyms, arguably not so useful in this context either, because you could relate things that aren't really very related by doing that. So yeah, usually it's just going up to become very generic and then going down to become specific. And if you don't have to go out very far, then arguably you have a fairly close related concept. So if you think about them as sort of sets of reference in the real world, and the sets getting very large as you go up, and the sets for the leaves then being very small, you can kind of think about it as like overlap of sets in Venn diagrams, and that the path distance is kind of describing how much we expect under some sort of assumptions of to simplify the problem, but how much overlap we'd expect there to be.
So traditionally, we only cover the hypothalamus.
Yes. Yes. Some fancier methods will do things like PageRank over the entire graph, but they'll have weighted different weights to downweight the other edges, so they won't treat all edges as the same. But even when we do just use these edges, which we expect to be very important, they're going to potentially be misleading at times. And they're going to be misleading around these entities and objects, right, at the top, because basically they're becoming very bleached of meaning once we get to that level. Okay, so one way we can do this is this idea of, in this Wu-Palmer metric, which is named after the people who created it, is the idea we'll look at the depths of these things. So let me just put that back on here. And I will switch it over. So in this case where, wait a second, I'll put the, hopefully I don't annoy people who are watching. I'll have them both up at the same time. Pretty sure it's recording this one and not the other one. But anyway. Okay, so in this case we're looking and saying the Wu-Palmer similarity between nickel and money, which is this one and this one, is going to be related to how deep they are. So I think this one's depth 1, this one's depth 2, 3, 3, 4, 5, and 6, right? So these are the depths, just how many jumps you have to make from starting with 1 as the root down towards the leaves. So if we look at the common ancestor of nickel and money, it's at value 2. Money is depth 3, and nickel is depth 6. So if we look back to the slides, does that make sense? Yes. So we have 2 on the numerator and 3 and 6 on the denominator. So this is where the numbers have come from, just to illustrate. So what that's basically saying is if the common subsumer is lower, it's going to give rise to to give us different numbers, for instance, in this formulation. If it's a very generic common subsumer, it's going to have a very low number for its depth. The similarity is going to end up giving us a lower value at the end. If the depth is very low in the hierarchy, this numerator is going to be bigger. It's going to end up giving us a higher value. And it's all relative to how deep the child nodes are, how deep the 2 leaves are that we're trying, or the 2 nodes are that we're trying to connect. So in this case, if we look at nickel versus money, we get the formulation that I just described, so we get 0.44. If we look at nickel versus Richter scale, you can see, if we go back here, so nickel versus Richter scale is a depth 3. Its common subsumer is the word standard. It's at depth 1. So we'll end up saying, whatever it was, 2 times 1 divided by 3 plus 6. Which is whatever, 2/9. Hopefully that's right, yes, which gives us a lower value. So effectively it's saying, even though these 2 children were at exactly the same depth in those 2 tests, because one of them had a higher root, it ends up with a lower number. It's less specific. Does that make sense? Okay, we're going to get on to a slightly more complicated method in a sec. Sorry. So the lowest common subsumer, let me make sure. Yeah, sorry. Let me come back. So the lowest common subsumer is basically saying if we have 2 nodes in a graph, what is the ancestor of those 2 nodes, the lowest ancestor of those 2 nodes? So the first, as we go up the tree towards the root in both cases, what is the first node that we're going to find that's on both paths? Path to nickel and path to budget in this case, right? And so the deepest node that we're going to find is this medium of exchange. So subsumer just means ancestor, and so lowest common ancestor here, the node that is general enough to cover both these concepts. Okay. Jump back. Okay. So let me go for time. Oh, good. Okay. So the next thing that we might want to do is go a little bit deeper and say that, hang on, just counting the edges isn't really going to give us a very clear idea of semantic distance. Sometimes some edges are more informative than others. Just counting how far they're away from the root might be not so good, right? So sometimes we might find hierarchies that are 10 or 12 elements deep. Other times they might only be 6 deep, but just because of the lexicographer decided that, I don't know, they wanted to separate out 3-pronged forks from 2-pronged forks, so they added in a special node in the middle, for instance. That's not necessarily informative. It's just a quirk of the data set. So it's not a great job of semantic distance, and so the Resnick and Lin method is a nice way of trying to resolve this. So this is a little bit more complicated, but the idea is that when we have this graph, this WordNet graph, we can basically go through it and say, for each node in the WordNet graph, if we look through it, all of the lemmas of all of the terms in that node and in all the descendants of that node, we can then count how often they occur in the corpus. So in the example that I have shown here, so we have entity. Now lots of things are entities. Almost every noun is an entity. So 40% of the corpus, the instances of words in the corpus, whatever corpus was used to get these numbers, were instances of entity. Now, in terms of instances of inanimate objects, so if we then go down a level and we say, let's look at all of the words that mean inanimate object or something more specific. So we'll get quite a long word list, just pulling them out, finding all the lemmas from WordNet, and we can then count them up. And we find that 17% of instances of words are inanimate objects, and so on down until we get all the way down to the bottom, and we see that the number of instances of the word hill, which is just going to be the raw count of the word hill now, is whatever this number is, very small. Lots of zeros and then a 1. Similarly, the word coast, it's pretty uncommon too. It's only occurred a few times, so that's how the unigram frequency of that word in the corpus. So if you were going to calculate this, it'd be painful. You go through the leaves first, you calculate their counts, you then aggregate them to their parents by summing up the counts of the children, and then you keep going up until you reach the root of this graph, and then you can normalize them and you get these numbers. So that's the first step. Let's attach to each node in WordNet how frequent the words of that concept are in a text collection. Step 2, we get this measure of information content, which is the negative log probability, which is sort of a way of encoding how surprised we would be if we saw this word. So this is like what we're looking at. This is unigram perplexity, in other words, right, for seeing a single word. And then we basically plug this into the previous formula, but we're swapping out counts now, depth in the graph for the information content. So what we do is we find the lowest common subsumer, as before. So the node that is the ancestor that's closest, that covers our 2 query nodes, and we work out its probability in the corpus, we frame that into information content, and then we do the same thing for the 2 child nodes. And so now what we see, and the point of this instance is kind of interesting, right? So we see that the word hill and coast, they have very low probabilities, but their parent node, their lowest common subsumer, geological formation, also has a fairly low probability. And that means they're all informative. And that means we're going to reward this and give them a very high similarity. Coast and hill are pretty similar according to this metric. Whereas if we were just using the depth, then we wouldn't get anything quite as nuanced. Because sometimes you can see here that if their common subsumer was natural object, they're going to get a value that's, you can see that this probability drops or increases by a factor of 10, so the log probability will go up by a constant factor. So it'll end up getting this penalty if we end up having to go an extra layer higher. So this is the kind of intuition that is encoded here. So effectively, it's a more nuanced version of depth by having sort of an information content as a mechanism. Hopefully that's clear. Yep.
So what is the corpus? Do you mean external corpus?
This will be an external corpus, like there's various corpora, like the Brown corpus. I think in the notebook we show an example. I think I'm not sure if we're computing this or computing some of the other metrics, but yeah, the idea is that you take a big corpus, large collection of text that's going to have each of the WordNet items at least 5 or 10 times each. So then you get some decent statistics for each of them. Yeah. Yes.
What's the capital N are we trying for?
The capital N, or the count of words in the entire corpus. So the number of tokens in say, the Brown corpus. So this is just a unigram frequency, right? It's just a question of what word list we're running this with. And if we're close to a root node in WordNet, it's going to be a very long word list. If we're at a leaf, it's probably one or maybe a few if there's a few lemmas attached to that synth set. Okay. Cool. Okay. So now how can we, I've sort of briefly motivated how we might use this, these ideas of distance. There are a whole lot of other ideas of distance. These were 3 distance metrics. These are kind of the more comprehensible ones. There's a whole cottage industry in these kind of metrics. Some of them better than others. But if we have this, how do we get back to our example, right? How do we work out that film and movie are similar? Yes?
You said that distance metrics. I'm just wondering if it's important for them to be metrics in mathematical sense.
I think that makes things a bit complicated. I think most of the methods proposed are not metrics in the mathematical sense. They don't obey triangle inequality and these kind of things. There has been, yeah, I'm talking off the top of my head now, but I believe there have been a few people who've proposed things to try and match that kind of intuition, because sometimes it makes sense, right? If something is synonymous with something else, you'd expect the inverse to apply as well, A to be synonymous with B and B to be synonymous with A. But if A is synonymous with B and B is synonymous with C, you'd like A to link to C as well. There's a question of how that generalizes, yeah, to language and various phenomena, but yeah, I believe there is work in that space, but I don't know if any of these measures are actually doing that. Okay. So what we can do is we can compare these words using WordNet paths of the various flavors we have. And so if we have something like K nearest neighbor, we can basically say, how close is this? We have 2 sentences. We look at the words. We say the word film in our second sentence. How close is that to any of the words in this is a great movie? And we might find that movie is the one we can get to most easily. And in doing so, we're sort of arbitrarily choosing a sense for movie, right? Because we're just trying to find the shortest path between these 2 lemmas. But by doing that shortest path, we can attach a number to this, and we can say that this is a wonderful film. Hey, we can get from wonderful to great in a few steps. We can get from film to movie in a few steps. So these are pretty close together. And that kind of thing can get reasonable. Well, there's a bit of engineering involved, but you could implement this inside KNN reasonably straightforwardly. If you wanted to do it in other types of classifiers, where you wanted to implement this as features, there's a whole field called word sense disambiguation, which is the idea you're trying to take a text and you're trying to automatically sense annotate each item. So wherever you see the word bank, you're trying to chuck a number next to it, say 1 through whatever, to say this is the WordNet synset being invoked here by this instance of the word bank. So this is a classification task, and it's quite a hard one. Okay, so there's an easier solution to this. This is one of the hacky popular solutions, is the idea of just finding which sense is the most common. A lot of words have one real predominant meaning and a whole lot of other very obscure meanings. By and large, when you use that word, you mean the standard one. So if you use the word bank, you probably mean the financial institution. You probably don't mean the riverbank. Now, I'm not sure whether or not that comes out from WordNet, but WordNet has counts attached to each of the senses, so you can actually say how often did this occur in data, in text, and you can use that to select which was the most predominant one. So that's one way of doing it, and then you have a way of sense annotating your data relatively approximately. You can take the minimum of senses if you're going to do this shortest paths idea, if you want to look at a similarity-based metric. But a better solution is actually treating this as a classification problem and trying to automatically run your classifier over text in order to do this classification. Okay, and there are a few ways we can do it. One is we can just use standard machine learning methods. So we might get some feature vectors by looking at the words to the left and the right of our word in question. Maybe we could look at the syntax as well, saying this is an adjective, this is the noun that it's modifying, this is the verb that it's relating to. You have to be, well, there are a whole lot of decisions here. It's very empirical as to what you choose, and lots of people have proposed various different feature templates for this kind of thing. In order to train this, you need sense tag data, and this was so I was mentioning SEMCOR before. There's another competition that's run for many years now called Sensival, where they run competitions on these kind of problems, and they've created a lot of data as part of that competition. This is very time-consuming, of course, but this is what you need if you're going to try and solve the lexical semantics problem in this way. Now, there are some less supervised approaches or unsupervised approaches. So one very simple one coming from 20 plus years ago is the LESS method. And the idea is you just look through this dictionary definition, so the gloss, and you see if any terms from the gloss can be found in the surrounding text. So when the riverbank says sloping land near water, as in its definition, you look for the word sloping and water in the context of the word bank in the corpus. And if you can find that, then you attach it to that sense. It works sort of okay, but it's nowhere near as good as a supervised method. Another approach is using this idea of self-training or bootstrap. So you create a very small training set. So for instance, if you're looking at plant here for factory versus vegetation, so you find some instances, say, of the phrase manufacturing plant and plant life, and you basically say that one is always the manufacturing sense, one is always the vegetation sense, and then you train a classifier to look at the context and predict one or the other, and then you use that classifier to identify more data that it can then automatically label and treat it as training data. And you do this over and over again. So this is called self-training in machine learning. There are a few other tricks that you can use alongside it. So there's an idea that if you use the word multiple times, you tend not to use it with a different meaning. If you have a sentence or a paragraph, you use the word bank several times in the paragraph, you're probably not jumping from one sense to another. You're probably invoking the same sense multiple times. And you can use that to make sure that this method doesn't get led astray and teach itself nonsense. It can, of course, so you have to hold its hand a little to make sure that it doesn't go silly. So the Rocky-O algorithm for pseudo-relevance feedback is another example of self-training in practice, where you're doing this in information retrieval. Okay. There are also various graph methods in WordNet where you use the WordNet graph, where you can use this to automatically label your corpus. So there's methods based around the PageRank algorithm from the original Google algorithm for doing web ranking, where you basically look at a whole lot of lemmas in text. So you have a sentence, you switch on those nodes in the WordNet graph, then you let information propagate over the WordNet graph, and you see which of the synsets got traversed more often than others. And you use that to decide that this word is likely to be this sense. So it's related to shortest path between pairs of nodes, but it's looking at the entire sentence as a whole and using the PageRank algorithm to do this. Okay. There are other lexical databases, one called FrameNet. It's talking about verbs. So it has frames for things like cooking, frying, baking, and boiling as examples of this idea of applying heat to something. So it's structured around a very limited vocabulary of verbs with specific meanings, and then it identifies that certain verbs need certain arguments. So if you use the word cook, you're basically saying there's a person usually cooking some ingredients, perhaps they're using some devices like saucepans and so on, and so each of these arguments is also described. So in some ways this is similar to WordNet, but it's not just saying cook is a verb and it has these meanings, it's also going a little bit deeper and saying this is how it relates to other terms in how it's going to get used with various arguments. And when we talk about syntax, we'll talk about how these words are used in practice. Okay. And so I'll wrap up with that. So the point here is that we've talked about how these knowledge-rich approaches using WordNet and other lexical databases can be used. They can be used to try as a starting point to try and work out how similar two words are to one another. But much more modern work is now looking at the distribution. So if we can see the word in practice used in a text, we can use that as a signal to do a lot of this automatically. And you can get, although WordNet has been developed over 20 years, in fact, you can extract from several billion words a lot of relationships that WordNet doesn't know about, which is kind of surprising. So yeah, I'll leave it at that, and we'll come back to that in the next lecture. Thanks.